Another important topic in the discussion of stereochemistry is actually prediction of the number of stereoisomers. And not only that, being able to draw them. And of course, the number of stereoisomers depends on the number of stereocenters present. Now we know already that, for example, the human hands are actually a natural pair of enantiomers. Yeah? So enantiomers are actually non-superimposable mirror images. If there is one chiral center, then it is possible to draw a pair of enantiomers. So enantiomers are actually stereoisomers. That's because there is one stereo center, so it's possible to draw two of them, and it just happens in that case for the two stereoisomers to be enantiomers. What if there is more than one chiral center or more than one stereo center? So how many stereoisomers possible? What if there are, for example, two chiral centers or three or four and so on? What is the number of stereoisomers? Well, there is a simple formula which is 2 to n, where n is the number of stereo centers, and of course 2 to n is the number of stereo isomers. So a number of stereo isomers is 2 to n, 2 to the power of n, where n is the number of chiral centers, if you like, or stereo centers. So if you take, for example, 2-bromobutane, you will see that this has only one chiral center. So therefore there are two stereo isomers possible. And of course, the two stereoisomers are actually enantiomers, a pair of enantiomers, which you can draw very easily. So let's do that actually. We can begin with drawing the specific chiral center. And of course, that's the chiral center here. The carbon number 2. And of course, if the exercise or the question is only how many stereoisomers, then that's easy. And if the question is how to draw them, it's very you are in control basically. So what you can do is you can do the easiest way, and that's to place the lowest priority group at the back. And of course, clearly on carbon number 2, the lowest priority group is hydrogen. So we have hydrogen, and then you can put Br anywhere. You can put methyl group anywhere. You can put the ethyl group anywhere. And remember, there is here in this case there is one chiral center or one stereo isomer, and therefore two stereo isomers. Two stereoisomers because there's one chiral center or one stereo center. So the two stereoisomers is this one they have to be, of course, a pair of enantiomers. So you draw one of them, and then very easily you draw the mirror image of it. So if you do that, then we get this. This mirror image. Clearly they are a pair of enantiomers, so there are stereoisomers, but they are a pair of enantiomers, and those are the only stereoisomers possible in this case. That's because there is one stereo center only, and they are a pair of enantiomers. You can actually double check the configuration if you want, and if you do that, they have to be opposite to each other. Enantiomers, of course, are opposite to each other in absolute configuration or in the direction of the rotation of a plane polarized light, as quantitatively measured by alpha d. Now, if you determine the absolute configuration here, obviously that's 1, this is 2, this is 3, and of course hydrogen is number 4. This is clearly clockwise rotation, that's R. If this is the mirror image, the correct mirror image of it, this should be S. Is it? Well, that's 1, 2, 3, and that's 4. And it's counterclockwise, so it is S. So that's actually good. Remember, there are two stereoisomers, and the two stereoisomers are actually a pair of enantiomers. That's because they are non-superimposable mirror images. So if there is one chiral center, then the number of stereoisomers are actually 2, and these 2 stereoisomers must be mirror images that are non-superimposable, and therefore they must be enantiomers. We will take other examples where there is more than one chiral center shortly.